In the fall of 2019, a flash drought impacted much of the southeastern United States, hitting Kentucky especially hard. At the beginning of September, 0% of the state was in drought, and by the end of the month, drought coverage was up to over 90%. Flash drought is a type of agricultural drought that develops very rapidly over the course of a few weeks. The key to flash drought is that precipitation deficits are coupled with persistent atmospheric anomalies, such as higher temperatures, stronger winds, or more sun. These persistent atmospheric anomalies drive an increase in evaporative demand. Think of evaporative demand as the thirst the atmosphere has for moisture. The increased thirst in the environment leads to the depletion of soil moisture and eventually vegetation stress that make it an agricultural drought. The Ohio River Valley is a major agricultural producer, with almost 50 million acres and farms across the watershed. Flash drought can lead to decreased yields, damaging crops and pastures. The patterns of excess moisture followed by drought the area has seen are expected to continue and intensify. Since Kentucky is a moisture-rich environment, flash drought early detection is very challenging. Forecasters want more tools to identify flash drought onset and provide early warnings to stakeholders. To help address these challenges, the NASA-developed team at the National Centers for Environmental Information in North Carolina partnered with the Kentucky Climate Center and NOAA's National Weather Service Ohio River Forecasting Center. The team analyzed and compared satellite-derived drought indices and gauge-based environmental data to better understand flash drought dynamics and guide early forecasting efforts. Drought indices are commonly used to forecast drought. They quantitatively categorize drought by combining data from one or more indicators. Currently, project partners do not use drought indices sensitive to flash drought in forecasting models, so the team compared two potential leading flash drought indices to the commonly used Standardized Precipitation Index and Standardized Precipitation Evapotranspiration Index. LARI, the Landscape Evaporative Response Index, models anomalies in actual evapotranspiration, essentially a reflection of land surface moisture available for plants in the atmosphere. And EDDI, the Evaporative Demand Drought Index, models anomalies in evaporative demand, that thirst the atmosphere has for water. The developed team downloaded the data, processed it to be a uniform resolution, and reclassified it to the U.S. Drought Monitor categories. An interactive ArcGIS Pro document was created for forecasters to assess and compare spatial and temporal patterns of the different drought index products. Time series of the percent area of drought categories and subwatersheds were also produced from 2010 to 2019 in order to further analyze the behavior of the indices at different events. EDDI exhibited more sensitivity, likely due to the meteorological variation of its inputs, but project partners identified it as a leading indicator and will now use it to raise their awareness of when to start paying closer attention to potential for flash drought. The Kentucky Climate Center houses the Kentucky Mesonet, a system of stations that collect climate and weather data across the state used for forecasting. Focusing on soil moisture, the team compared ground measurements by the Mesonet to satellite-derived data from NASA's Soil Moisture Active Passive Satellite, or SMAP. SMAP collects data across the globe to estimate surface soil moisture measurements.
The Mesonet provides us point observations where we have our stations located, while that remote sensing data helps to fill in the mosaic and add more context and detail to what's happening in Kentucky. That's particularly valuable to us.
The analysis showed that SMAP and Mesonet measurement values differed, but displayed similar patterns of wetness and dryness. The team used these comparisons to help the Kentucky Climate Center identify which stations had better patterns of agreement.
I think the biggest value of this work is going to be increased confidence. That is, we'll have a better picture and more reliable information. This increased confidence will help us to be more proactive in terms of addressing issues.